In this video, we'll be covering logarithmic differentiation. This first function here looks really problematic. Notice how there's three different binomials, 1 to the power of 3, 1 to the power of 2, 1 to the power of 5. First off, we do not want to multiply this whole thing out. That would be a nightmare and a half, even just if we had to the power of 3, let alone to the power of 5, and two other terms with it. So we definitely don't want to multiply this out, which again, algebraically, if we're trying to find the derivative, that is one thing we could do first, multiply everything out. So we're definitely not going to try that method. The second way that we could currently do this problem is by utilizing the product rule. But again, notice, if I use the product rule, that means I've got to group these two things together, and those two things have their own product rule, with a chain rule, given that there's a 2 and a 3 at the powers. And then after I've taken the product rule of those two pieces together, I've got to treat that whole thing right there as one function, and take it as a product rule with the 6x minus 5 or minus 7 to the power of 5 function. So that means I'd have to do two product rules with three different chain rules in everything here, and that's just a nightmare to do in and of itself as well. Well, there is another thing that we could do. Now remember, one of the things that we can do to functions is appropriately manipulate the function algebraically first. Well, I'm going to go ahead and first start by changing this f of x to be a y. That is my first step in simplifying this entire function. My second step in simplifying this entire function is thinking of all of the rules that I have for algebra, as well as the functions that are not necessarily algebraic but transcendental functions as well. Hopefully in the last section of material you reviewed your rules for logarithmic and exponential functions. Well, remember, one of the rules for exponentials and logs, specifically logs, is that x times y is the same thing as the natural log of x plus the natural log of y. Now you're thinking to yourself, well, how is this ever going to help us? I mean, I don't want to introduce logs to this problem. Well, by looking at this function, if I were to take the natural log of both sides, okay, that means I take the natural log of everything here on both sides of the equation. Sorry, I should probably use a bracket on that one. Next, I can identify, well, any multiplicative piece will change into the addition of separate logs. So that means that this is going to be the natural log of x minus 3 to the power of 3 plus the natural log of 2x plus 4 to the power of 2 plus the natural log of 6x minus 7 to the power of 5. Now again, this, you're thinking, why does this make this thing any better? Well, keep in mind another rule that we have for log functions is x to the power of p. If the variable and the power are both inside the log functions, I know these don't look like they are inside, but they are inside. If this was a power on the log function as a whole, that 3 would be there, not here. But the rule is that that power can drop down in front. Again, this is not calculus, this is an algebraic rule for the logarithmic functions. These are rules that can be always applied to any log function without taking any derivatives or doing any real math at all. So that means that this 3 can be pulled down in front. So now I have 3 natural log of x minus 3 plus 2 natural log of 2x plus 4. And then right here I have plus 5 natural log of 6x minus 7. With all this being done, this is all equal to the natural log of y, and I may again apply implicit differentiation, which means I'm going to simply, I don't have y equals, but I will take the derivative of both sides of this equation. Now this form of implicit is actually a little bit smoother than the other versions that we've played with. What's the derivative of the natural log of y? Well, remember, the derivative of natural log of anything is 1 over that anything times the derivative of the inside, which is going to be dy dx in this particular case. Okay, so that's the first side. I've taken the derivative of natural log of y and I've gotten that. Now over here, you're looking at this going, I don't want to take the derivative of this, but to be honest, we didn't want to take the derivative of this function to begin with. We didn't want to algebraically manipulate this function to begin with. And I don't know about you, but taking the derivative of the natural log of x minus 3 seems a lot easier than everything else that we might have been able to have to do. So I'm going to carry down the constant, because that's always allowed, multiply it by the derivative of the natural log of anything. Okay, again, the derivative of a constant times a function is the constant times the derivative of the function. Well, the derivative of natural log of anything is 1 over that anything. And just to be safe, what is the derivative of x minus 3? Always check the interior function. The derivative of x minus 3 is 1. So I'm going to put that there just so that I know it's there, but that right there is the derivative of that term right there. Plus, I'm going to carry down that plus sign. The derivative of 2 natural log of 2x plus 4, again, carry down the 2. The derivative of natural log of anything is 1 over that anything. And then again, don't forget to check the chain rule, the derivative of the inside. What is the derivative of 2x plus 4? Well, that's a 2, so I've got to add that extra 2 there. So again, notice this 2 carried down. This natural log of anything is 1 over that anything, and then the derivative of the inside gave me 2. Plus, carry down the 5, the derivative of natural log of anything is 1 over that anything, times the derivative of the inside, which is 6. So now you'll notice I simply have a bunch of fractions. I know. It's much worse than having polynomials, but this, I think, is still much worse than dealing with this, because this stuff right here, I have 1 over y times dy dx is equal to, this simplifies down to 3 over x minus 3. This thing simplifies down to 4 over 2x plus 4. Yes, that can be simplified further, but I'm not going to. Plus 30 divided by 6x minus 7. And you'll notice, what was the goal of this problem? Again, it was to solve for y equals, which means dy dx equals to this thing multiplied. If I multiply both sides by y, I then get that thing all by itself, that dy dx. So these two things cancel out, and I have dy dx equals to 3 over x minus 3 plus 4 over 2x plus 4 plus 30 over 6x minus 7 times my y. But I'm going to backtrack here and recall that my y is this entire function. Because I know what y is equal to in terms of x, I should replace y with what it is in terms of x. So it is multiplied by x minus 3 cubed times 2x plus 4 squared times 6x minus 7 to the power of 5. And again, we could go ahead and distribute this into all three of these terms and simplify as much as possible, but that just seems like a lot more work than we want. The skill here is to remember how to use the logarithmic functions and their properties to manipulate a basic function that looks obnoxious algebraically into something that we can easily take the derivative of. That right there is logarithmic differentiation. Let us do one more example of logarithmic differentiation such that I have b to the power of x. This logarithmic differentiation will allow us to actually take the derivative of any base here. So if I had, say, y 10 to the power of x versus y e to the power of x. Now this one here is simply just going to be e to the power of x. That derivative is smooth, it's simple, it's straightforward. This one, however, is not nearly as simple. So I'm going to go ahead and do this example. This is 3c, and then I'm going to go ahead and follow up with showing you that one. So the derivative of y equals b to the x. I'm going to take the natural log of both sides because I don't like that ugly power being on the base of b. That power of x can drop down in front by using the logarithmic rules. Now keep in mind, I have done no calculus here yet. First step, take the natural log of both sides. I'm going to put those parentheses in there. Second step, I can pull the power down in front because the natural log function tells me I can do that. Third, I will now take the derivative. Okay, the derivative natural log of y is going to be 1 over y times dy dx equals the derivative of x times the natural log of b. Now, sure, b seems like a variable in this problem. It is not. B is something like 10 or 3 or 5 or 7. We don't know what that number is. But we know that b stands for a constant. So the natural log of a constant is a constant. So what's the derivative of x times a constant? Again, if I had y equals 3x, the derivative of 3x is 3. So the derivative of x natural log of b is natural log of b. Now we've got one extra step. Remember, dy dx has to be all by itself, so I have to multiply both sides by y, which means dy dx in the end is equal to y times the natural log of b. But remember, if I know what y is, I must replace it. b to the x, natural log of b. Now, if you look at this example over here, e to the x, you will notice that if I apply this rule, it's if I have y equals b to the x, then the derivative is b to the x natural log of b. This is the derivative. So if I have that little trick, that means then this one right here will become e to the x natural log of e. But what is natural log of e? That's just 1. So this rule doesn't change because of this format, which means that all of these rules should apply. So for this right here, the derivative will be 10 to the power of x natural log of 10. That will be my y prime.